Imagine you trained a machine learning model and it gives you 95% accuracy. You might think, great, my ML project is done. But what if I tell you that your model can have 95% accuracy and still be completely useless in the real world? Maybe you solved the wrong problem. Maybe your training data doesn't represent real users. Maybe your model works perfectly in a notebook but fails when deployed. Or maybe it works today but becomes inaccurate 6 months later because the real world data has changed. This is why becoming an ML engineer is about much more than learning algorithms. You need to understand the entire machine learning project lifecycle. In this video, we are going to follow a machine learning project from the initial business problem all the way to production and monitoring. In previous videos, we built our foundation. We understood what machine learning is, how models learn from data, and the different learning paradigms such as supervised, unsupervised, self-supervised, and reinforcement learning. Now we are moving from concepts toward actual ML engineering. Today we are going to understand how a real ML project is built. This is the complete picture that I want you to remember throughout this series. Machine learning is not simply collecting data, then making a model, and then predicting. There are many steps in between. And after the model is trained, our job isn't finished. We still have deployment, monitoring, and eventually retraining. So think of machine learning as a continuous life cycle, not a one-time model building exercise. The first mistake beginners make is starting with an algorithm. They ask, should I use random forest? Should I use XGBoost? Should I use a neural network? That's not where an ML project starts. It starts with a business problem. For example, imagine an e-commerce company has noticed that many customers are stopping their purchases. The business problem is customers are leaving. Before we build anything, we need to understand why this matters to the business. Now we convert the business problem into an ML problem. Instead of simply saying we want to reduce churn, we define a prediction problem. For every customer, we want our model to predict whether that customer is likely to churn. Now we have a machine learning problem, binary classification. This conversion from a business problem into a well-defined ML problem is one of the most important skills of an ML engineer. Now we need to define our target. What exactly does churn mean? Does it mean the customer hasn't logged in for 30 days, 60 days? Did they cancel their subscription? Did they stop purchasing? We need a precise definition. For example, we could define a customer is considered churned if they haven't made a purchase for 90 days. Now our target becomes something measurable. Churns equals 1 or 0. We can make the objective even more useful. Instead of simply predicting yes or no, our model can output a probability. Customer A might have an 8% probability of churning. Customer B might have 73%. Customer C might have 91%. Now the business can prioritize customers who are at high risk. Another important question is, how do we define success? This is when ML engineers need to think beyond accuracy. The model may have good precision, recall, or F1 score, but ultimately the business might care about reducing churn and increasing customer retention. So we need both machine learning metrics and business metrics. This distinction becomes extremely important later when we evaluate real production systems. Once we understand the problem, we need data. Data could come from many places. We might have customer information in a database, purchase history in another database, application logs, website activity, mobile app events, external data sets. An ML engineer needs to understand how these different sources can be combined into a data set suitable for training. In tutorials, data sets often look beautiful. Real world data usually doesn't. You can have missing values, duplicate records, incorrect data types, outliers, incorrect labels, inconsistent values, and one of the most dangerous problems, data leakage. We will come back to leakage because it can make a model look excellent during development while being completely unreliable in production. Before training a model, we need to understand the dataset. What does one row represent? What does each column mean? Which column is our target? How many examples do we have? Are values missing? Are there duplicate records? How are the values distributed? This stage is often called exploratory data analysis or EDA. EDA helps us understand what's actually inside our data. We might calculate summary statistics, look at distributions, examine correlations, investigate outliers, and importantly, understand our target distribution. EDA isn't just making charts because charts look nice. The goal is to discover information that can influence our modeling decisions. Here is an important example. Suppose only 5% of customers churn, 95% don't. If our model simply predicts nobody will churn, we could get 95% accuracy, but the model is useless. This is why we cannot blindly rely on accuracy. We need to understand the actual distribution of our target. Next comes data cleaning. We may remove duplicates, correct data types, handle missing values, remove or investigate invalid records, and determine what to do with outliers. But remember, cleaning does not mean blindly deleting anything unusual. An outlier may be an error or it may be an extremely important real observation. We need to understand the domain before deciding. Missing values are common, but there isn't one universal solution. Sometimes we can remove rows, sometimes we can fill numerical values with a median. For categorical values, we might use the most frequent category. Sometimes more sophisticated imputation is appropriate, and sometimes the fact that a value is missing is itself meaningful. So we might create a separate missing value indicator. Now let's discuss one of the most important concepts in the entire ML lifecycle: data leakage. Leakage happens when information that would not actually be available at prediction time accidentally enters the training process. Imagine we are trying to predict whether a customer will churn, and one of our features is the customer's cancellation date. Of course, the model will perform extremely well, but that's cheating. At the time we make the prediction, the cancellation date doesn't exist yet. So the model learned from information about the future. Feature engineering means transforming raw information into features that are useful for machine learning. For example, instead of simply giving the model the last login date, we can calculate days since last login. Instead of providing hundreds of individual purchases, we might calculate average monthly spending, purchase frequency, or number of purchases in the last 30 days. Good features can make a huge difference to model performance. Imagine the raw login history tells us that a customer logged in on January 1st, January 5th, and then February 20th. Instead of forcing the model to interpret dates directly, we can engineer a feature such as days since last login. This feature may provide a much clearer signal about customer engagement. Now we need to split our dataset. A common approach is to have three sets: training data, validation data, and test data. The exact percentages are not fixed. The important idea is that each data set has a different purpose. Training data is what the model learns from. Validation data helps us make decisions during development. We might use it to compare hyperparameters or models. And finally, the test dataset should be treated as an unseen dataset for final evaluation. The test set is essentially our final exam. Suppose we train and test on exactly the same data. The model may perform extremely well because it has already seen those examples. That's not what we want. We want to know whether the model can perform well on new unseen data. This ability is called generalization. Before jumping into complicated algorithms, we should create a baseline. A baseline gives us something to compare against. For example, perhaps our baseline simply predicts the majority class. Or we could use a simple logistic regression model. If our fancy model doesn't meaningfully outperform a simple baseline, we need to ask whether the additional complexity is justified. We actually train our model. The algorithm uses training data to learn parameters. It makes predictions. We compare predictions with the actual targets. We calculate a loss, and an optimization algorithm updates the parameters to reduce that loss. This process repeats over many iterations until the model learns useful patterns. Here is another distinction you need to understand. Parameters are learned from the training data. For example, neural network weights. Hyperparameters are settings we choose before or during training. Examples include learning rate, tree depth, number of trees, path size, and so on. Later in the series, we will go much deeper into hyperparameter optimization. After training, we evaluate our model. But again, there isn't one universal metric. For classification, we might use precision, recall, F1 or ROC, AUC. For regression, we might use MAE, MSE, RMSE. The metric should be connected to the problem we are solving. If you don't understand any term, please don't worry. We will cover everything in the upcoming videos. Right now, those things are a little bit complex for us to understand right now. For classification problems, one of the most useful tools is the confusion matrix. We have true positives, false positives, false negatives, and true negatives. These four values form the foundation for metrics like precision, recall, and F1 score. We will study these in much more detail in a dedicated video later in the series. Precision and recall answer different questions. Precision asks, why my model predicts positive, how often is it correct? Whereas recall asks, out of all the actual positive cases, how many did my model find? Which one matters more depends on the business problem. And this is why simply saying my accuracy is 95% doesn't tell us enough. Once we have a working model, we can improve it by tuning hyperparameters. We might change the learning rate, tree depth, number of estimators, regularization strength, and then evaluate the different configurations using validation data. Later, we will explore techniques like grid search, random search, and more advanced optimization approaches. One of the biggest problems during model development is overfitting. The model performs extremely well in training data but poorly on unseen data. Essentially, it has learned the training examples too specifically instead of learning patterns that generalize. An advanced ML engineer needs to constantly think about generalization. The opposite problem is underfitting. Here the model performs poorly even on training data. Maybe the model is too simple. Maybe the features are not informative. Maybe the model hasn't been trained enough. So our goal isn't simply maximize training accuracy. Our goal is to find a model that generalizes well. Once we are satisfied with our model, we need to deploy it. This is where ML engineering becomes very different from simply building a notebook. We need to make our model available to applications, perhaps through an API, a web service, a batch pipeline, or an embedded inference system. The model now becomes part of a real software system. Imagine our application sends a customer ID to our prediction service. The service retrieves the required features, processes them exactly as expected by the model, sends them into the model, and returns something like churn probability 87%. This is an example of online inference. But not every ML application requires real-time predictions. Sometimes we can process data in batches. For example, every night we might calculate churn probabilities for 1 million customers. This could be significantly simpler and cheaper than running a real-time prediction service. So the architecture depends on the business requirement. This is one of the most important lessons for anyone who wants to become an ML engineer. Deploying the model does not mean the project is finished. We need monitoring. Is the service responding quickly? Are there errors? Has the incoming data changed? Are predictions changing unexpectedly? Is model performance dropping? ML systems can degrade over time, even if the code hasn't changed. One reason a model can degrade is data drift. Imagine we trained a model using customers mostly between 20 and 40 years old. 6 months later, the business starts targeting customers between 50 and 70. The production data now looks different from the training data. the model may no longer perform as well. This is one reason monitoring is essential. Another important concept is concept drift. Here the relationship between the input and target itself changes. For example, customer behavior could change because of a new competitor, new pricing, a new product, or a major market event. The patterns the model learned previously may no longer represent today's reality. ML projects often involve many experiments. We may try different models, features, and hyperparameters. We need to keep track of these experiments. Otherwise, after running 50 experiments, we won't remember which configuration produced which result. Experiment tracking helps us compare and reproduce results. Imagine you trained an excellent model 6 months ago. Can you recreate it today? If the answer is no, that's a problem. Production ML requires reproducibility. We need to know which code, data, features, configurations, and environment were used. This becomes especially important when working as part of an engineering team. Now let's put everything together. We start with the business problem, collect and understand the data, prepare it, train the model, evaluate it, deploy it, monitor it. If the model continues performing well, we continue. If we detect degradation or drift, we investigate, retrain, and potentially deploy a new model. That's the real machine learning lifecycle. A notebook where you train a model successfully is not the same thing as a production ML system. A production system requires data pipelines, validation, versioning, deployment, monitoring, and maintenance. This is the gap that an ML engineer needs to learn how to bridge. This is the mindset I want you to develop throughout this series. Don't just ask, what's my accuracy? Ask, is this actually the right problem? Is the data trustworthy? Is there leakage? Does the model generalize? Can another engineer reproduce it? Can we deploy it? Can we monitor it? And what happens when the world changes? If you are working on a real ML project, this checklist is a useful mental model. You don't necessarily execute every step exactly once. Real projects are iterative. You may go back to the data after evaluating a model. You may redefine features. You may change the target. You may discover that the original business problem wasn't properly defined. That's normal. Machine learning development is iterative. If you remember only one thing from this video, remember this. Machine learning engineering is not train a model, calculate accuracy, and you are done. It's a complete system. We start with the problem, we understand the data, build a model, evaluate it, put it into production, observe what happens in the real world, and continuously improve it. So today we covered the entire machine learning project lifecycle. We started with the business problem, converted it into an ML problem, collected and explored data, cleaned it, created useful features, split the data, built a baseline, trained and evaluated models, tuned them, deployed them, monitored them, and finally we discussed retraining. This is the foundation for everything we will build from here. In next episode, we are going to zoom into arguably the most important component of machine learning, data. We will understand structured and unstructured data, features and labels, data quality, sampling, bias, missing values, outliers, leakage, and pre-processing. Because remember, garbage in, garbage out. If the data is bad, even the most sophisticated model won't magically fix the problem. So I'll see you in the next episode.